radio frequency radiation can be used to connect and power wireless devices simultaneously, enabling them to become battery-free. Simultaneous wireless information and power transfer, or SWIFT for short, has long existed in wireless communication literature as a concept. In SWIFT, we are faced with a hard decision, and that decision is how we split the power between the information receiver and the rectifier, which converts the incident radiation into useful DC power, which ultimately powers the whole system. In our work, we proposed the first antenna which allowed us to perform SWIFT across two different frequency bands using a rectenna which does not need an impedance matching network. And this design is based on a simple microstrip patch antenna, and we implement it using flexible materials, using e-textile conductors for wearable applications.
Here at Southampton we do a lot of work on electronic textiles, which is where we put electronic functionality into otherwise standard fabrics, and a consistent challenge with these systems is powering them, and they all too often rely on rigid conventional batteries for their supply of power. The work we've done on energy harvesting, and in this case RF energy harvesting, is an essential ingredient towards making these systems autonomous and removing that requirement for rigid power supplies. Another requirement is obviously supplying or communicating the data from these systems. And the work we've done in this paper is both tackles the energy harvesting aspect as well as the communicating the data as well.
Starting with a simple microstrip patch antenna, and just like any other wearable antenna, our antenna can operate on the human body and communicate with a high gain in radiation efficiency and complying with the absorption limits. The novelty in our design comes from how our second port of the antenna is integrated. Our port uses an inductive loop and dipole-like radiating arms. And thanks to the inductive design of the second feeding port, we do not need a matching network, so the complexity is significantly reduced and the cost is significantly reduced. And in terms of power conversion efficiency, our design compares very well to state-of-the-art antennas. In fact, it improves the efficiency by more than 50%. We have shown that the same topology can be applied to more complex antennas, meeting the requirements of different wireless communication applications. We have demonstrated that SWIFT could happen in the same band and not just over two different bands, using a 4-port microstrip antenna, which combines the benefits of dual polarization communications for MIMO resistance and full duplex with the convenience of dual polarization power transmission, where we do not need to care about the alignment between the transmitter and the receiver. We believe that using our array of SWIFT antennas, wireless powered networks, wireless powered body area networks can take a big step forward in integrating them in future real-world applications based on multi-band and multi-polarization diversity antennas.
Hello everyone. So the research topic is a switchable multi-coil antenna with booster coil to improve coverage in WPT systems. The authors of this work are from Indian Institute of Technology, Ropar, and our laboratory is Antenna and Microwave Lab. So straightly we will go on to the proposed design. So the proposed design, first we will see at the figure B. So that is the proposed transmitter coil we have built for the wireless power transmission. So here we can see at the center there is a chief coil, and at the edges we can see there are booster coils. So what happens is when the receiver coil is perfectly aligned, then only chief coil is excited, as you can see. So you can see there is a receiver coil at the figure A where it is perfectly aligned, and there is a dotted receiver coil which is the misaligned receiver coil. So the moment there is a misalignment, then what happens is we will also on the booster coils along with the chief coil, so as to maintain same amount of magnetic field to the receiver coil, so that the induced voltage and mutual coupling will be same for the perfectly aligned receiver coil as well as for the misaligned receiver coil. So the same we can see in the equivalent circuit diagram. In the right side we can see, right top. So when the switch is on by using a control circuit, then what happens is we are actually short circuiting the booster coil path and only allowing the chief coil to be operated. So when only chief coil is operated, that means the receiver coil is perfectly aligned. So that is called mode 1 operation, as we can also see in the text below. So when the switch is open using the control circuit, then what happens is these both chief coil and booster coils will be in series connected, and both will form a widespread uniform magnetic field, so as when the receiver coil is misaligned in any direction, then it will receive same amount of magnetic field, so as to maintain same voltage. So now we will discuss about few results. So as we can see, the top figure is magnetic field distributions. So in the top figure, figure A represents mode 1 magnetic field, that is concentrated magnetic field due to only chief coil, and the B figure at the top represents the uniform magnetic field when the booster coils are also on along with the chief coil. So at the below also we can see there is a mutual inductance, so when under mode 1 as well as under mode 2 operation. So now we will see the experimental setup that we have used. So for experimental setup, we have used a robotic setup, a vector network analyzer, and a fabricated coils. So what we used to do is, generally we used to connect the transmitter coil to the port 1 and receiver coil to the port 2, and we used to measure S parameters. And finally we will see the conclusion. So here we can see uniform magnetic field region of literature design is 51.84%, whereas proposed design is 17.65%. Similarly, uniform mutual inductance also, ours is 23.04% compared to 6.25%. Thank you.
Hello everyone, my name is Edoardo Negri and I am a PhD student from Sapienza University of Rome. This video briefly introduces our latest publication on transactional antennas and propagation, which deals with the leaky wave analysis of innovative resonant assembly launchers used in a wireless power transfer scenario. Leaky waves are modal solution of partially open waveguides. They are characterized by a complex wave number whose real part, beta, the phase constant, is related to the radiation angle, and the imaginary part, alpha, the attenuation constant, accounts for the longitudinal decay and determines the beamwidth. While the modal field in 1D leaky wave antennas can be represented through a linear superposition of exponentials, in 2D leaky wave antennas it is given by outward and inward angle functions. As the superposition of exponential envelopes with the same amplitude generates sinusoidal functions, an inward and an outward cylindrical wave give us a Bessel distribution. Indeed, Bessel beams are a focusing solution of the Helmholtz equation given by a spectral superposition of plane waves with wave numbers lying on the surface of a cone. With respect to other focused beams such as Gaussian beams, they can maintain their transfer resolution for large propagation distances, a very important feature for imaging applications. In addition, their self-healing property is of crucial importance in point-to-point communications to allow for non-line-of-sight operation. In brief, Bessel beams are nowadays of great interest for the antennas and propagation community. An effective way to generate Bessel beam at millimeter wave is by exciting a cylindrical metallic cavity, whose top metallic plate is replaced by a partially reflecting sheet to allow for radiation. Such structures are commonly known as resonant Bessel beam launchers and mainly exist in two types, TM and TE polarized. Regardless of depolarization, the operating principle is the same. A dipole like source generates an outward cylindrical leaky wave, which is reflected on the circular metallic rim, giving the desired inward propagation. At this point, having the needed components, it is possible to generate the Bessel beam distribution by enforcing a constructive interference of them through amplitude and phase conditions. One of the key points of this work is the rigorous analysis of the radiating performance of Bessel beam launchers with hybrid TE and TM polarization character. This operating condition is typical at sub-millimeter frequencies where purely TE or TM sources are hard to find, and conversely, Bessel beam launchers can be more easily excited through a quasi-resonant slot, which represents an horizontal magnetic dipole. The theoretical description of this innovative structure deals with the excitation of both TM and TE leaky waves and the evaluation of their different excitation coefficients. The latter are rigorously evaluated with closed-form expressions obtained from a residue analysis of the relevant Green's function of the structure. With this expression at hand, it is possible to design a hybrid polarized Bessel beam launcher to resonate at a given frequency with the TE or the TM leaky mode, as well as in non-resonant condition. In each case, an impressive agreement has been achieved among full wave and theoretical results. Among all the possible applications of bezel beams, we have shown on the paper the possibility to generate wireless power transfer links between two resonant bezel beam launchers. They operate in the radiative near-field region, showing better performance with respect to reactive and far-field links in terms of working distance and efficiency, respectively. In particular, hybrid polarized bezel beam launchers operating in either TE or TM resonant conditions give interesting results comparable with previous solutions available in the literature. On the other hand, when operating in non-resonant conditions, the link shows a slightly lower wireless power transfer performance. More details can be found in the paper, and we will be happy to answer you any question you may have by mail. Thank you very much for watching.